Good morning. Can everybody hear me at the back? Good. I hope to give you an overview on good local exhaust ventilation, and my presentation really applies to local exhaust ventilation in general. So I think we've heard mainly about welding fume today, but I have gone for a general route because the design of LEV applies to all substances. So what is LEV? It's an engineering control system designed to reduce exposure to airborne substances such as contaminants as dust, mist, fumes, vapours or gas. It's covered under the Control of Substances Hazard to Health regulations, and they require you to prevent, or we can't do this, to adequately control exposure. Sorry, I apologise. This is just a basic diagram of an LEV system. You would have a hood where the contaminants are drawn in. You have a ducting which carries the contaminated air through the ductwork, through a fan, a particular filter or an air cleaner to clean it before it goes through the fan and out to discharge. To work effectively, LEV systems need to be designed and suitable for the work. Installed and commissioned properly, routinely checked and maintained throughout the year, tested and thoroughly examined at least once every 14 months or more frequently if they're listed in Schedule 4 of COSH regulations. Check that they still work when they're moved or altered and used properly. And HSE have produced guidance, it's HSG 258, and it gives detailed guidance on how to design and the process of choosing the right LEV system, and it provides all information on routine checks and thorough examination and test, and that will be covered later. So design of an LEV system, it has to be considered, and to achieve effective control you need to think about the contaminant cloud, the work process and the operator requirements, and the type of LEV hood. You need to know what you're controlling. You need to know the processes and the sources in the workplace that give rise to airborne contaminants, their hazardous substances and their properties, and how gases and vapours and dusts, fume and mists rise and how they move in the surrounding area. There are 4 general types. Sorry, just go back slightly. Buoyant, which would be heat or fume, whether the contaminants injected into moving air, such as a spray gun, dispersed into the workplace through natural ventilation and air movement, and directional, which would be caused by the direction of the work tool, such as hammering or chipping, rotating discs or cutting saws. You also need to know the principles of good LEV design and how to apply these to the process and the contaminant source. Think about the needs of the operator and those working in their vicinity. How to design LEV for ease of use and for safety in checking and maintenance. And also to prepare an LEV manual, a specification for performance checks, a logbook and a schedule for thorough examination and test. LEV systems work most effectively when the contaminant cloud is contained, received or captured at source. The effectiveness can be judged by how much the hood constrains the contaminant cloud, how well the air flow is captured and contained and carried into the system, and how little contaminant actually gets to the breathing zone of the operator. Now, the breathing zone is the operator's face, and it's usually defined as within 30 centimetres of their mouth and nose. So you really don't want the fume to reach that. This slide here shows us the capture zone. The first picture on the left-hand side, you can see the person chipping stone is working within the yellow bubble, so that would be the capture zone. But as he progressively moves away from it, the capture falls off. So the further that you move away from the LEV point, the less effective it becomes. As a rule of thumb, if a duct diameter or hood diameter, you reduce your effectiveness by about 10%. The capture velocity is defined as the velocity required to overcome the movement of the contaminant cloud and draw it into the hood at a defined working distance. So, for example, on the right-hand side, where the largest distance away he is from the hood, you need to define that, and the capture velocity has to be effective to control there as well. So choice of hood and enclosures are critical. The various designs, shapes and sizes, they control the contaminant cloud in 3 different ways and fall into 3 basic categories: enclosing hoods, receiving and capturing hoods. Enclosures are almost always more effective than capturing or receiving hoods. Now, a full enclosure would be where the process is completely enclosed, for example, a glove box, or a room enclosure where you would have blasting or paint spraying cabins, and these type would have the operator within the room, and he would have to have special protective, respiratory protective or air-fed protection. So some diagrams or pictures. Partial enclosure in the first slide. That's typical of a walk-in spray booth. The operator and the parts would be positioned in the centre of the area. He would stand to the side and he would spray in the direction of the extract. To the right-hand side, it's typical canopy hood for hot processes. The heat will rise and will have direction and speed generated by the process, and it'll move towards the canopy hood. These can be fixed or movable. Here we have a capturing hood. On the left-hand side, it's at a fixed welding bench. The one in the middle and to the right-hand side are typical of the movable arms. The process is outside the hood, but the hood has to be correctly positioned as close to the source as possible. It has to have sufficient airflow to capture and draw the contaminant into the hood and away from the operator. And you can see in the middle photograph how well that's done. Capture hoods also include rip or limb ventilation, known as slot ventilation, downdraft tables or benches, and low volume, high velocity LVHV hoods. And this would be typically on tool extraction using low volume, high velocity. Welding fume, you can see in the middle photo, the fume's not extracted when you have an extraction on, but once you apply the extraction, it's significantly reduced. Okay. Hood selection and design are critical to the process and the performance of an LEV system. They must match the process, the source, the production, and how the operator carries out the process. General rules are: maximise the enclosure of the process and source, because the greater the degree of enclosure, the more likely the LEV will be effective. Position the capture and receiving hoods as close as possible to the process and source, and take advantage of the direction of the speed and airflow produced by the source. Match the hood to the size of the process and the contaminant cloud, and separate the contaminant cloud from the worker's breathing zone as much as possible. Think about how the worker actually does the job and apply ergonomic principles when designing the LEV. And try it out, make a prototype and get back feedback from users. Use observation and techniques, look at how they're working at it, look at good practical and simple methods such as smoke and dust lamp to assess exposure and to control effectiveness. And I haven't on the slide here, but one important thing is install airflow indicators at the hood to show that it's working properly. For higher risk materials and a higher potential of exposure, and where it's critical that LEV is necessary to be maintained at all times. Then sampling should be carried out to assess the airborne exposure to make sure that the LEV is actually doing what it's designed to do. And this would usually require a hygienist. Okay. The next slide, the next series of slides are a set of photographs. And really, I've concentrated on this one in particular, dust, but the design principles apply to all substances hazard to health in whatever way you design the LEV. This is a sieving room, and basically it's a room enclosure, and it has, let's see, here, sliding door, you have your sieve, mechanical sieve, and an LEV hood. The doors were kept closed when the operation was in process. So if you think about what I was saying before, does the hood match the source, and is it suitable? To the right-hand side, you see the LEV hood, and you see the baker on the left-hand side lifting and tipping sacks of materials or powder into the sieve. So the first thing I would ask was, why do they even need to sieve the material in the first place? Could they not have enclosed the process? The LEV hood is too far from the source. It's not even the correct shape or design to contain it or pull it towards it. So it doesn't match the process or the source. Second, does it match the work activity? Well, we mentioned ergonomic processes. He's lifting and tipping sacks above shoulder level, so it hasn't been thought through. And why does his head have to be in the plume of dust? Does the container capture the dust? Well, the answer is no, because you can see it has spread out into the room. He also bends down into the container, so why does he have to do that? So all these questions have to be asked when you're thinking about design and control. Does it capture dust and exposure from all activities? The bag opening is far away from the exhaust, which is useless anyway, so it just won't capture it. But it hasn't been considered because he has to open the bag, lift it and carry it over to the sieve. Can that not be automated, or can they not bring materials in that are less dusty, or do they even need to sieve at all? I just draw to your attention to the operator. He has a hairnet on, he has glasses, he's got hearing protection, and he's a P3 mask on. And they're all uncomfortable to wear when you're working and doing that heavy manual lifting. But if you notice where the straps and the RPE are, they're both of them around the back of his neck. One should actually be up over the back of his head, and one should be around the back of his neck, and it should be securely tightened. It's actually not fitted correctly. It's not providing a face seal, and it's providing no protection. So we've mentioned COSH before, and it requires you to prevent or adequately control exposure, and the key word is prevent. So as I said before, why do they even need the sieve? Well, you can't apply appropriate control measures, and that means design and use appropriate work processes, systems and engineering controls, control exposure at source, and provide adequate ventilation systems. So I think this is probably an add-on to their existing system, and none of the design principles have been applied. Okay, the hood design is critical, and once you have that correct, then design the rest of the system. The ductwork connects the components of the ventilation system and carries contaminated air through the system to the discharge point. Keep the design as simple as possible. Use smooth bore ductwork and keep it free from obstruction, internal obstruction. Minimise the length of horizontal runs and keep the lengths of flexible ducting as short a length as is practical to use effectively. Provide sufficient air velocity to keep the particles suspended in the duct so that it won't settle out. And you have to think about noise issues here as well, because if you high velocity going through metal ducting, it creates a racket. Provide test holes for measuring and duct velocity. Keep the number of bends and junctions to a minimum to reduce airflow. Don't use T-junctions, and changes of direction should be smooth and at a small angle, and where you need to change the size of the cross-section duct, it should be smooth and tapered. And you need to provide dampers to adjust a balance or flow in different branches of the LEV system. Ducts inside the building should be under negative pressure, so if it leaks, then it's inward into the duct. Route ductwork to minimise noise nuisance, and provide drainage points at any low points in LEV systems where you have aerosols, mists or substances that may condense or support combustion. Provide access points for cleaning, inspection and clear blockages. You should mark and identify the ducts, including test points, and place hazard warning signs to notify people what the duct contents of the duct may be. And depending on the temperature range, it should accommodate thermal expansion and contraction. So air cleaners remove the contaminant before it's discharged. Particle collectors are the most common type and include fabric filters, cyclones, electrostatic precipitators and scrubber systems. The fan provides the power to move the air. It draws air in and the contaminant moves along the duct and then to discharge. Some centrifugal fans would be the most commonly used for LEV because they are capable of creating a large difference in pressure, produce big airflows. The propeller fan often is used for general dilution ventilation, but it's not suitable for ductwork or dusts. The fan location, the objective would be to keep as much ductwork under negative pressure. So it's located and as close to the extract as possible. And indoor ductwork upstream of the air mover should be under negative pressure. I've mentioned that before, just to prevent leakages. So discharged atmosphere, that's normally via a stack or a chimney. The extracted air must not re-enter the building or re-enter other buildings unless the contaminant level is such a low or negligible concentration. The discharge duct has to be high enough and located well enough above the highest point of the building to ensure that it's drawn away by the external atmosphere and doesn't re-enter. And it must be at a high enough speed to ensure that it's dispersed. Avoid rain caps and other devices that reduce the vertical velocity, and never use devices that direct the discharge downwards. Recirculated air is often used to save energy and reduce heating and cooling costs, and that's acceptable as long as it's thoroughly cleaned. The air cleaner must match the contaminant and the concentration, and there's no point in putting in an organic filter to remove, organics, a carbon filter to remove organics, because it won't take out dust, and vice versa. A dust filter will not extract organics. Recirculation is easier where you have particles of low concentration and or lower toxicity materials. And if you have a recirculation system, we'd advise you to have monitoring and alerts. Okay, when you've designed your LEV system and you install it, it has to be installed and commissioned. It has to be installed properly, and it has to be commissioned. So that commission is really confirming that it's capable of doing and providing adequate control and doing what it was meant to do. Verify that the system was installed and as designed. Show that the LEV system meets the specified technical performance, and assess the control of effectiveness. That means demonstrating that it's containing the materials that it was designed to do. Then you also have to produce a user manual, a logbook and a commissioning report. Now, I refer to HSD 258 because chapters 8 and 9 of that document are very detailed in what you need to do. It's freely downloadable from the HSE website, and I would advise people to have a wee look at it. So to demonstrate adequate control, you need to assess the control of effectiveness. This step's not often done. It's one of the things that's missed out. People install it, they commission it, they're getting the right airflow, but is it actually positioned properly and in the right place? So what you need to do is observe the process and the operator. And you use tools, simple tools such as smoke tubes to visualise the direction of flow and how effective the capture is, or a dust lamp to highlight particles or fume which you can't see with the naked eye. You have to think about what quantities of dust and fume are produced. Is it captured effectively? Is it drawn into the hood, or does it spread into the operator's breathing area? Is there settled dust lying around, or are there eddying currents and dead zones? Do the operators work inside the capture zone? And if not, why not? Is there a reason why they can't do that? Is it not possible for them to physically work near to the hood? Does the hood not move, or do they not want to move the hood? Check for leaks and, where necessary, carry out air sampling. So once the LEV system is installed and commissioned and checked that it's working effectively, then you need to keep checking, maintaining and testing it. That includes routine checks. After any modification, you have to service it and maintain it within the manufacturer's recommendations. And again, thoroughly examine and test at least every 14 months or as specified in COSH. Now, I'm not going to cover any more on thorough examination and tests because a colleague's going to do that later. But we're getting to near the end of the slides. So what I would say is you have to have a competent supplier for all stages of the process, from designing, installing, commissioning and thorough examination and test, and including in-house maintenance and routine checking. There are various organisations out there that can provide you with information and training courses and qualifications. The HSE website has loads of information on it. Qualifications can be gained through the BOHS, CIBSE or LEV membership. I know I've put these in as shortened form, but I'm happy to, I can't remember, British Occupational Hygiene Society, Chartered Institute of Building Service Engineers and Industrial Local Exhaust Ventilation. We have details of these in packs outside. And again, my last slide, the British Occupational Hygiene Society run 2 courses, a P601 for thorough examination and test and a P602 for basic design principles. Not plugging them, but they're very useful to go to get an overview. You have sort of a qualification and an understanding at the end of it. And again, the sources on the HSE website are worth visiting. So thank you for listening.